Hello everyone, welcome to my YouTube channel. So today I am going to discuss the complete linear algebra solution for CSIR NET December 2023. Okay, so I will mention the question ID as previous videos. I hope this video will be helpful to all of you. Thank you. So let's start. So the first question ID is 704028. So the question says that I'm not going to write the whole question. So question is given that it is a matrix A such that the ijth entry is product of I and j. So which of the following is the eigenvalue of A? So if I write down the matrix looks like say n, then 2 times 1, 2 times 2, 2 times 3 and so on. So 2 times n, and here it is n times 1, n times 2, n times 3 and so on. It is n times n. So observe that rank of A is 1. Why is it? Because n times the first row is same as nth row. So if you do the row operation, you can do that nth row minus n times first row, n minus 1th row minus n minus 1 times first row, and so on. So in this way you will get that rank of A is 1, which is quite simple. If you don't understand, then take n to be 3 or 4 and write down the matrix and do the row operation. You will understand. So rank of A is 1. That means trace is same as trace of A equal to non-zero eigenvalue of A. So rank of A is 1. That means it has at least n minus 1 0 eigenvalue. So only left eigenvalue may be 0 or non-zero. But since the trace is non-zero, that means trace of A is equal to the non-zero eigenvalue. Trace of A is equal to the non-zero eigenvalue. Now what is trace of A? Trace of A equal to summation I square I equal to 1 to n, which is same as n into n plus 1 into 2n plus 1 by 6. That means only non-zero eigenvalue is this and all the other eigenvalues are 0. So option 4 is correct. Okay, move to the second problem. Okay, so question ID 704027. So which one of the following statements is true? If A is a real 3 by 2 matrix and B is a real 2 by 3 matrix, then rank of A less equal to true and rank of B less equal to 2, right? Because it is 3 by 2 and 2 by 3 matrix. So rank is less equal to minimum of this m and n. So rank of A less equal to 2 and rank of B less equal to 2. And we know that rank of AB and rank of BA both are less equal to minimum of rank A and rank B. That means both have rank less equal to 2. Now rank of AB. Now AB is 3 by 3 matrix, right? Because A is 3 by 2 and B is 2 by 3. So product is 3 by 3. And BA is 2 by 2. So AB is 3 by 3 matrix and rank of AB less equal to 2. Hence AB cannot be identity matrix. So first one is false. Okay. AB a real matrix which is 3 3 1 2, and if B is its inverse, then B has to be 2 minus 1 minus 3 3 times 1 by determinant of A. What is one determinant of A? It is 3. So 1 by 3 times 2 minus 1 minus 3 3. So B doesn't have integer entries. That means second one is also false. What about third one? If A equal to 3 1 1 2 with entries in Z6, okay, in Z6. So here the entries are from Z6. Then there exists a matrix B with entries in Z6 such that AB equal to identity. So check determinant of A. So determinant of A is 6 minus 1 is 5. Now 5 is invertible in Z6. That means 1 by determinant of A, which is equal to 5 inverse, exists in Z6. This will imply A has an inverse. Right? This will imply A has an inverse. So third one is correct. What about fourth one? If A is a real non-zero 3 by 3 diagonal matrix, then there exists a real matrix B such that AB is identity. Non-zero diagonal matrix, so you can put one diagonal entries as 0 and other to be any non-zero value. Then it is non-zero diagonal matrix, but it doesn't have inverse. It has no inverse because 0 is an eigenvalue. It is not invertible. Okay. Move to the next problem. This one is also so simple problem. So 704029. Product of two 2 by 2 real matrices of rank 2 is of rank 2. That is true, right? Because A has rank 2 and 2 by 2 matrix. B has rank 2. So rank is full. That means they are invertible. Invertible. That means their determinant non-zero. So AB is also invertible. So AB has full rank. That means AB has rank 2. Product of two 3 by 3 real matrices of rank 2 is at most rank 2. Right. Because rank of AB less equal to minimum of rank A, rank B. That means this is also true. Product of two 3 by 3 matrices of rank 2 is of at least rank 2. So what is the other inequality for rank of AB? Rank of AB is greater equal to rank A plus rank B minus n. So n is here n equal to 3 and rank A and rank B are 2. So rank of AB is greater equal to 2 plus 2 minus 3, which is 1. Hence third one is false. What about fourth one? Because third one saying that it is at least 2, but here we are getting 1. The product of 2 by 2 real matrices of rank 1 can be 0 matrix. That is true. You can particularly take A to be 0 1 0 0 and B to be same as A. Then A square equal to 0 matrix and A has rank 1. Hence third option is false. Okay. Go to the next problem. So the next problem is saying that 704031, this is the ID number. Okay. So let we have a notation of kind of inner product, that is a symmetric bilinear form on R2, and there exists a non-zero V and W such that the bilinear form V comma V. Okay, this is the notation. This is the symmetry. This is the bilinear form on R2, and it is given that this is greater than 0, this is greater than 0, and this is 0, and A be the 2 by 2 real symmetric matrix that representing this bilinear form. That means if I write down this bilinear form as H, it is same as H of x comma y equal to x transpose AY, where A is a real symmetric, because this is symmetric bilinear form. Then which of the following is true? Okay. So I can diagonalize A, right, and write it as P transpose D Py. It is same as Px transpose D Py. Now A is a real symmetric matrix. So we have two non-zero vectors such that for one we get greater than 0 and one we get less than 0. That means A is not positive definite as well as A is not negative definite also. So we have, and A is real symmetric matrix. That means one of its eigenvalue is positive and another one of its eigenvalue is negative. So eigenvalue of A equal to say lambda 1 and lambda 2, then lambda 1 greater than 0 and lambda 2 less than 0. So in particular we can write H of xy as say x bar transpose dy bar, where x bar equal to px, y bar equal to py, and D is the diagonal matrix. D is the diagonal matrix, lambda 1 0 0 lambda 2. Fine. Now we are checking the options. This is the theoretical result. Okay, so D equal to lambda 1 0 0 lambda 2. Now we are going to check the option. So it is saying that a square equal to 0. That is not necessarily true. In particular, you can just take a to be minus 1 0 0 1, right, and a to be minus 1 0 0 1, and define a symmetric bilinear form, say H of xy equal to x transpose ay, right, and clearly you can see that 1 comma 0 1 comma 0 is minus 1, which is less than 0, and 0 1 0 1 1 greater than 0. So this satisfies the given condition, but a square is non-zero. A has rank of A is 1, that is also false, because here A has rank 2, and rank of A is 0, that is also false. Now only fourth option left, so fourth one is correct. Now how do I prove in general that there exists such vector, right? So in particular, after diagonalization, you can think it as some x bar transpose dy bar. So H of x comma x is given by x bar transpose dx bar. Say it is x1 bar, x2 bar, lambda 1 0 0 lambda 2 times x1 bar, x2 bar. So we'll have lambda 1 x1 bar square plus lambda 2 x2 bar square, right, where lambda 1 greater than 0 and lambda 2 less than 0. So since lambda 2 less than 0, so replace it by say lambda 1 x1 bar square minus lambda 2 x2 bar square, and think lambda 2 as positive number. Okay, then I need to find whether there exists some u such that satisfies this condition, right? So if it is 0, that will imply lambda 1 x1 bar square plus lambda 2 x2 bar minus lambda 2 x2 bar square equal to 0. So in particular, take x1 bar to be say 1 and x2 bar root over lambda 1 by lambda 2. Okay, then this becomes 0. Hence there exists some vector which is non-zero vector that satisfies this condition, right? And after getting x1 bar and x2 bar, you already know p, because this is D, right? So you already know p. So px equal to this matrix times this, right? Then you will have the actual value u. Okay, so then you will have actual u which is non-zero, such that this happens, right? So that's why fourth one is correct. Okay. Now move to the next problem. So the problem is, this is the very interesting problem. This is the very interesting problem. So the question ID number 704030, A be a n by n complex matrix. If n greater or equal to 4, then which of the following statement is true? So you need to know some basic result from linear algebra. See, C is an algebraically closed field, right? Algebraically closed field. That will imply that any polynomial splits. So this will imply any matrix is triangulable. Why? Because we know a theorem. This is a very important theorem. If you don't know, you can just check Hoffman-Kuhn's book, that any matrix over C is triangulable. What is its meaning? If the matrix is A, then A can be written as P inverse JP, where J is upper triangular matrix. Or in particular, since if you know Jordan canonical form, in particular you can take J to be the Jordan canonical form of A. So any matrix over C, you can write its Jordan canonical form. So J is an upper triangular matrix, right? Now the options are very easy. So now if you take any, so if A equal to P inverse JP, what is its meaning? You can think A to be a linear map. A is a linear map from Cn to Cn with respect to a standard basis, right? So whenever we have a linear map with respect to given basis, we can take its matrix representation. Conversely, if we have a matrix representation, we can think it as a linear map with respect to some basis. So I am taking A to be a linear map from Cn to Cn with respect to standard basis. Now if A is similar to J, that will imply J represents, say this linear map is T, represents T with respect to some basis. Right? So say J is equal to same as T with respect to some basis B. Okay. So now if I write this basis as say U1, U2 up to UN, and if I write J to be, say here it is lambda 1 something this, 0 lambda 2 something this, 0 0 lambda 3 something this, and so on, then you can see U1, say this is V1, this is an invariant subspace. Why? Because T of U1 equal to lambda times U1. V2, say the subspace generated by U1 and U2, it is span of U1 U2. This is also invariant subspace. Why? Because T of U1 equal to lambda 1 times U1 and T of U2 equal to some A, here it is say A12 times U1 plus lambda 2 U2. So that means span of U1 U2 is an invariant subspace because image of T of span of U1 and U2 is same as is contained in span of U1 and U2. In this way, Vk equal to span of U1, U2 up to Uk. That means you will have invariant subspace of any dimension starting from 1 to n. Okay. So option 1 is clearly false because you can take the obvious two invariant subspace is always the full space Cn and the trivial vector 0 because image of 0 is 0 under any linear map, as well as the full space Cn, image of Cn is contained in Cn. So that means A is clearly false. All the eigenvalues of A are real number, that is also false because the matrix is a complex matrix. You can take in particular I 0 0 I, right? That the eigenvalues are I, but this is not real number. And A has an invariant subspace in Cn of dimension n minus 3. That is true because starting from 1 to n, we have invariant subspace of any dimension, and that we can make by using its triangulable form. By you can think the Jordan canonical form. Okay, so that's why it has also invariant subspace of dimension n minus 3. So second one is correct, and A square is also a complex matrix. So A square also have the same property because A square can be written as P inverse J square P, but J square is also a triangular matrix. So A square doesn't have any invariant subspace of dimension n minus 1. That is also false. So second one is correct. Fine. Move to the next problem. So this problem I don't want to waste time because this is just a computational problem. Okay, so for some value of A, you need to find whether it is positive definite or not. Just find the characteristic polynomial and check the conditions on A, and if all the eigenvalues are positive, then it is positive definite. If not, then depending on the values of A, you can just conclude. This is just a computation problem. Okay, so move to the next one. Okay, so the ID number, question ID number 704076. Suppose 7 by 7 block diagonal complex matrix has blocks 0, 1, 0, 1, 0, 0, 2 pi I, 1, 0, 0, 2 pi I, 0 and 0, 0, 2 pi I. These are the blocks. 7 by 7 diagonal matrix, diagonal complex matrix that has blocks. Observe that this is a block, this is a block, this is a block, this is a block. But if you see it properly, most of the students did the same mistake, that if you see it properly, these are not the Jordan blocks. These and these are Jordan blocks, but fourth one, this is not a Jordan block, because if it is 3 by 3 Jordan block, then there must be a 1 here. So here it is actually a 2 by 2 Jordan block and then a 1 by 1 Jordan block. Okay, so that's why it is very important. Now you can just use the property and get. So what are the property? First of all, what are the eigenvalues? What are the algebraic multiplicity of the eigenvalues? So algebraic multiplicity. For 0, algebraic multiplicity is 3. Here is 1, here is 2. For 1, the algebraic multiplicity is 1. For 2 pi I, the algebraic multiplicity is 3. So that means characteristic polynomial is x cube times x minus 1 times x minus 2 pi I cube. Hence first one is correct. Now, so you can think that, so this is already in the Jordan canonical form. So the Jordan canonical form, if you check the Jordan canonical form, here you will get that for 0 Jordan block, What about the Jordan blocks? For 0, 1 by 1 block and 2 by 2 block. For 1, 1 by 1 block. For 2 pi I, 1 by 1 block and 2 by 2 block. Right? And all the blocks occurs exactly one times. So that means, what about the minimal polynomials? So we know that if there is some minimal polynomials for some lambda, if the minimal polynomials have the power that x minus lambda power k, if minimal polynomial has factor x minus lambda power k, that means it must have at least one Jordan block of k by k order for lambda, right? So that means the minimal polynomial, the given minimal polynomial is false, because in the given minimal polynomial for 2 pi I the factor is x minus 2 pi I cube. That means there must be at least one 3 by 3 block corresponding to 2 pi I. But here the largest block for 2 pi I is 2. This is the minimal. So that's why this cannot be the minimal polynomial. This one is the false. Now, dimension of eigenspace for lambda is equal to number of Jordan blocks. So that means dimension of eigenspaces for 0, 1 and 2 pi I is 2, 1 and 2, because number of Jordan blocks for 0 is 2, number of Jordan blocks for 1 is 1, and number of Jordan blocks for 2 pi I is 2. So 1 and 4 are correct. Okay. So these are the basic properties from Jordan canonical form, and by using that you need to solve this, and the same type of problem comes in every time. Okay, move to the next one. So the next problem, question number 704072. This is the ID number. So T from R5 to R5 the linear transformation, and suppose that the three vectors span the null space of T. You can just check that these three vectors are linearly independent. That is your work. I don't want to waste this time. So you can just check these three vectors span the null space, and this is linearly independent. That means nullity is 3. So rank is 2. Option 1 is correct. And also you can check the fourth one, that some vector is contained in null space. You can write that vector as linear combination of that given vector in the question. So checking 1 and 4 is simple. I want to explain the second and third option. So we have rank of T is 2. Okay, fine. Now it is given that suppose that for every vector V there exists a n such that T power nv is 0. So say T power k1 of E1, say E1, E2 up to E5 standard basis. T power k1 of E1 is 0, T power k2 of E2 is 0, and T power k5 of E5 is 0. Let k be maximum of k1, k2 to k5. Then T power k of ei is 0 for all I, and since this is the basis, that will imply T power k of v is 0 for all v belongs to R5. So in particular T power k is 0. This will imply T is nilpotent. So T is a nilpotent linear map. So since it is nilpotent linear map, so that will imply T power 5 is 0. Right? Okay. Now you will use the Jordan canonical form. Right? How do you use that? So t power 5 is 0 and nullity equal to 3. That means number of Jordan blocks for 0 is 3. So what are the possible Jordan blocks? Possible Jordan blocks is 2 2 1 3 1 1. Right? Because number of Jordan blocks is 3 and sum of the order of Jordan blocks must be 5. So these are the possible Jordan blocks. Okay. Now if you choose this one, okay, then second one definitely false, because it is saying that t square must be 0, but t square is not 0 here because it has a 3 by 3 block. If you have a 3 by 3 block, then this block is say j, that means j cube equal to 0 and j square not equal to 0, because it is 3 by 3 block, Jordan block. Hence second one is false, because t square may not be 0 in this case if I consider this Jordan block and corresponding the matrix. But third one is definitely false, because if t square is 0, that means t cube is also 0. Hence third one is correct, because if I take third one, then 3 by 3 Jordan blocks getting killed up, so third one is correct. Hence 1 3 4 are correct option. This is also a nice application of Jordan canonical form. So if you have crystal clear concept of Jordan canonical form, then you can answer this problem. This is a very interesting problem, but basic conceptual problem. Move to the next one. The next problem is 704073 ID number. X, y be two n by n real matrices such that x, y equal to x square plus x plus identity. So clearly x into y minus x minus identity equal to identity. From this I can claim that x is invertible, because x times some matrix is identity, that means x is invertible. Okay, so if x is invertible, then y can be written as x inverse times x square plus x plus identity, hence xy equal to yx. Okay, what about third one? Third one is saying that x plus I is invertible. So xy minus x square equal to x plus I, same x plus y minus x equal to x plus identity. So x is invertible, but y minus x may not be invertible, right? X is invertible, but y minus x may not be invertible. So in that case, x plus identity is not invertible. In particular, you can take x equal to y equal to minus identity. Then it satisfies that condition, and x plus I is 0 matrix, so that is not invertible. And fourth one is y is invertible, but that may not be true, because take x to be, say, this matrix, take x to be a matrix such that x square plus x plus identity is 0. So take this one, okay, say x is this, right, and then y equal to 0 matrix. Then x square plus x plus identity is 0 and xy is also 0, but y is not invertible. Hence 1 and 3 are correct option. Fine, it's a very nice problem. Also 704074, I don't want to waste time. What you need to do, first you have given a 1423, find its characteristic polynomial. It is CH polynomial. 1 minus lambda times 3 minus lambda minus 8 is 0. So lambda square minus 4 lambda minus 5 equal to 0. So lambda square equal to 4 lambda plus 5. That means you can write lambda cube, lambda power 4 and lambda power 5 as combination of lambda and the constant term. Hence there is a given expression, you can put that, and you can put instead of lambda, since this is by Cayley-Hamilton theorem, that will satisfy the matrix equation. So a square, we have a square equal to 4a plus 5. From that we will have a cube equal to some constant a1 times a plus some other constant, and you can just do this, and finally you will get a and b from given condition and check the conditions. This is quite easy. So simple problem, very simple problem. Okay, move to the next one. This is a fine problem. So to do that, you need to know a very important result from linear algebra, that any n by n real symmetric matrix is diagonalizable, right? And eigenvalues are real. So A is diagonalizable and all eigenvalues are real. That is directly from the theory. And second and third option is also correct, because if a power k is 0, that means minimal polynomial of a divides x power k. Now a is diagonalizable if and only if minimal polynomial has linear factors, right? It has distinct linear factors. Here only the linear factor is for eigenvalue 0. That means minimal polynomial of a equal to x. Hence a is 0. So a square is 0. So third one is also correct. And a power k equal to identity. So minimal polynomial of a must divide x power k minus 1. Right? And only real roots of x power k minus 1 is 1 and minus 1. That means it must divide x square minus 1. Hence a square equal to identity. That is also true. So all the four options are correct here. It is very simple problem, but you need to know the properties of real symmetric matrix and its diagonalizability. Fine. Move to the next one. So the ID number 704071, let F be a finite field and V be a finite dimensional non-zero F vector space. Which of the following can never be true? I think this same problem came in many times in different exams. So V is not union of its proper subspace. V is not union of its proper subspace. Let V equal to U union W. Okay, where U and V both are proper subspaces. So let X belongs to U such that X doesn't belongs to W, and Y belongs to U such that Y belongs to W such that Y doesn't belongs to U. So X belongs to U, Y belongs to W. So X belongs to V, Y belongs to V. Since V is a vector space, X plus Y belongs to V. Right? Now X plus Y belongs to V means implies X plus Y belongs to U or X plus Y belongs to W. If X plus Y belongs to U, that will implies Y belongs to U. Why? Because this is a subspace. So I can write Y equal to X plus Y minus X. X plus Y is in U, X is in U, so Y must be in U. That is a contradiction. As well as if you write X to be X plus Y minus Y, X plus Y is in W, Y is in W, so that will imply X is in W, which is also a contradiction. Hence, V cannot be written as union of its proper subspace. Union of two proper subspace. Now what about many more? Right? You can do that. So in particular for finite field, say F, the field to be, say take Z2, and finite dimensional non-zero vector space, say V is given by Z2 direct sum Z2, two-dimensional vector space over Z2, sorry, over Z2. Now take the subspace V1 as 0, 0, 1, 0, V2 as 0, 0, 0, 1, V3 as 0, 0, 1, 1. Take all of its union, you will see that this equal to V1 union V2 union V3. So it is union of three proper subspaces. Okay. So second one is correct, first one is false. V has unique basis. That is also false, because dimension of V is 2, right? Here you can take basis to be 1, 0 and 0, 1, as well as 1, 0 and 1, 1, 1, as well as 0, 1 and 1, 1. So it is not necessarily have unique basis. So third one is also false, and fourth one is also false, because we have already 3 bases here. But V has precisely 2 bases, that is also false. So that's why only option 1 is the correct answer here. Fine. Move to the only option 1. Only option 1. Though it is an MSQ problem, but only option 1 is correct. Okay. Move to the next one. So A be a real diagonal matrix. So again the ID number is 704077. Let A be a real diagonal matrix with characteristic polynomial lambda cube minus 2 lambda square minus lambda plus 2. Define a bilinear form on R3. Which of the following is true? So the characteristic polynomial is lambda cube minus 2 lambda square minus lambda plus 2. Is lambda cube minus lambda cube times lambda minus 2 minus 1 times lambda minus 2. So lambda equal to 2, 1, minus 1. So A is positive definite, that is false, because minus 1 is an eigenvalue. A square is positive definite, definitely, because eigenvalue of A square is 4, 1 and 1. Rank of A is 2, that is also false, because it's an invertible matrix. So rank is 3. And there exists a non-zero vector V in R3 such that the bilinear form V transpose AV, so say let V equal to V1, V2, V3, right? So V transpose AV equal to V1, V2, V3 times 2, 0, 0, 0, 1, 0, 0, 0, minus 1, V1, V2, V3. So it's same as 2 V1 square plus V2 square minus V3 square. So take V to be 0, 1, 1. Then V transpose AV 2 into 0 plus 1 minus 1, which is 0. Hence, this is 0. The bilinear form V comma V, that is 0, and V is a non-zero vector in R3, 0, 1, 1. Hence, 2 and 3 are correct. Move to the next one. I don't know whether there is any other problem. Let's check. Yeah, there is a nice one. I think this is the last problem. Yes, this is the last one. Consider the quadratic form Qxyz is given by x square plus xy plus y square plus xz plus yz plus z square. So from a given quadratic form, what is quadratic form? Quadratic form means if you have a bilinear form and hx comma x is given equal to qx, right? If x is a vector, here I think it is better to write hv comma v equal to qv, where v equal to the vector xyz. So that means it is given by some v transpose av, and the matrix A is given by, if you if you have this quadratic form, then it is given by the quadratic term. The coefficient of the quadratic term are diagonal entries 1 1 1. I think you all know, because this is a important theory from quadratic form. And the coefficients of other terms, say the coefficients for the xy terms, by 2 will be here. So 1 by 2 and 1 by 2 here. For xz, 1 by 2 and 1 by 2 will be here. For yz, 1 by 2 and 1 by 2 will be here. So this is the matrix. Fine. So this is the matrix. Now if you check the eigenvalues, what are the eigenvalues? First of all, row sum is 2, so 2 is an eigenvalue, and another 2 eigenvalue, half and half, you can just compute. Okay, half and half. So that means A can be written as P transpose this, right? Fine. So fourth one is correct, because the quadratic form is given by an invertible real symmetric matrix, which is this one. And now let's check the first three one. So if you have a vector, this one, say V, then and v1 v2 v3 times 2 0 0 0 half 0 0 0 half v1 v2 v3, and if you multiply it, you will get 2 v1 square plus half v2 square plus half v3 square. Clearly, if you take any vector from Q3, this will be greater or equal to 0. This cannot be 0 unless v1 v2 v3 are 0. That means there doesn't exist any non-zero vector such that from rational coordinate, that means from Q3, such that this is 0. Similarly for R3, but from C3, if you choose v equal to, say, what should I say, you can take anything, like, okay, you can take, say, v1, it is 0, say 1, say I, then 2 times 0 plus half times 1 plus half times minus 1, which is 0, and this is a non-zero vector. So there exists a non-zero vector u from C3 such that quadratic form for u is 0. Hence third one is also correct. So 3 and 4 are correct. I hope this video is helpful to all of you. I will upload the real analysis solution within 2 days. Thank you.